we did not do number 2 together, right? I don't think that we did. So we'll do number 2 together. Grab some markers. Okay. So here we've got a ramp, and instead of the ramp going upward, the ramp is going downward. This is just a symbol that for whatever reason gets stuck in my handouts, and I have to go through and delete them every year. I don't know what's up with that. Anyway, so it says now we have a ramp that's tilted downward, and the sphere leaves the ramp at 1.5 meters per second, as shown below. The bottom of the ramp is 1.9 meters above the floor. Calculate the range of the sphere. So I had some students in the last day or so ask me things like, well, how do I know what I'm supposed to do in order to get the correct answers? And so what I've been telling them, and this is what's a good idea, is you first want to make a list of what you know and what your other variables are. So you're going to make a list of your variables first. If you can't solve for the thing that you're being asked to solve, the next thing you want to do is try to solve for time. Because since time is the thing that that can be used in either the horizontal variables or the vertical variables, that's the one that you can solve for to help fill in gaps where you need to know more information to be able to get to your ultimate answer that you want. And then solve the problem. Will be the last step. So with this one, we're going to start by making a list of variables. So for our list of variables, we're going to have horizontal things, horizontal. And the only things that we can have for horizontal are our range, time, and our initial horizontal velocity. We actually can't know any of those yet. We're going to have to solve for them. For vertical stuff, things that we always know that acceleration is minus 10 meters per second squared, unless the problem says something like, but you're not on Earth, you're on Mars or the moon or Jupiter or something, and your acceleration is whatever. We also know that the distance that our object is going to fall is 0.9 meters. So we know that our delta y, our change in y, our change in vertical position is minus 0.9 meters. One thing that we can solve for is our initial vertical velocity. And ultimately what we're being asked to solve for is our range of our sphere. So it looks like that if we've got our list of variables, the next thing to do is to solve for time. We don't have anything to help us so far with our horizontal stuff, so we can't use that to solve for time. And if we were using it to solve for time, we would already have the range. So we're going to use time to solve for the range. Down here, we can solve for time if we know what this initial velocity is, and the problem does give us enough information to be able to do that. So if we look up here at our picture, I'm going to draw, I'm going to extend my horizontal line, and I'm going to draw this line that'll be the path of my object as it comes off the ramp. It makes this curve because it's going to accelerate. The downward velocity is going to accelerate, which is going to make it kind of veer off this diagonal trajectory that it was on. But what we want to know is what the velocity is as it leaves the ramp, because if we know our horizontal and vertical velocities, then that will help us out a lot. So horizontal, and the way that I do this is I think about it like it's a box. So this is my initial horizontal velocity. This one is my initial vertical velocity. And I also know that because of congruent angles, that this 15-degree angle, man, hold my pen better. This 15-degree angle ends up in between the orange and the purple line. Like that. All right, so I can solve for these velocities. If I want to solve for my initial horizontal velocity, the relationship between the orange line and the purple line is those are adjacent in terms of this 15-degree angle. So adjacent angles would be the cosine. So the cosine, excuse me, the cosine of 15 degrees is going to be equal to that initial horizontal velocity divided by the velocity of the total vector here, which we're told is 1.5 meters per second. So that initial horizontal velocity is going to be 1.5 meters per second times the cosine of 15 degrees. You can just in your calculator make sure that you're in degrees and not radians. So I've got 1.5 times the cosine of 15. So my initial velocity here is 1.45 meters per second, which is a lot of it, right? So if we look at that, we're going to, geez, that's awful. That's awful close to 1.5. The reason it's so close is because this angle is so shallow. And so that's okay. So I'm going to take that information, I'm going to write it here in my list so that I know that I have it, and at a glance I can tell how much information I have here, if I'll be able to solve anything with those equations. You guys have any questions so far? Used to this trig stuff? You guys feel comfortable with the trig stuff for the most part? Yeah, I think that using triangles and trig to solve physics problems is like all that I remember from trig from high school. That, and it was hard and I did not enjoy it. Maybe some of you enjoy it. So for the other one, I'm going to have a similar form. I'm going to have the sine of 15 degrees to solve for my vertical. And I'm going to swap this out for the vertical thing. So, after a while, you notice some patterns. Like I could just go straight to this. 1.5 meters per second times the sine of 15 degrees is going to give me my vertical velocity. So I just switched out the trig. Is it an identity? I forget the right vocabulary. My trig identity, and then I swapped out my variable over here. So that's going to be 1.5 times the sine of 15. So there we get 0.39 meters per second. Not a whole lot. Write that down here. Okay. So I've got those two pieces of information. But look, now I have 3 pieces of information in my vertical variables, which means I can start to solve for things. Unfortunately, it means I have to use a quadratic formula. So next I'm going to solve for time. So we've got my change of y equals 1/2 acceleration times time squared plus initial vertical velocity times time. We know that our change in height is 0.9 meters, which is equal to 1/2 times minus 10 meters per second squared times time squared. So I was reading a blog of a teacher that I know, and he was talking about something that in New York, the state of New York, is called the Regents exam. And so on the Regents exam, I'm not sure how he has awareness of this, if he's involved in the grading or if he just was able to get access to a rubric. But on those exams, there are, it's kind of like an end of course exam. And so students have to demonstrate their ability to be able to complete physics problems and other sorts of problems. And we may have discussed this a little bit, like whether or not to keep units in the equation. And the way what you have to do to get the maximum points on those problems is either include all of your units across the equation as you complete it, or make a list stating what all your values are. So at least for that state, for their tests, having this list of variables helps you so that you don't have to pay quite as much attention to having your units over here. If you guys are planning on doing engineering courses in college or STEM courses and that sort of thing, I'd encourage you to keep up the practice of keeping your units in the equations, because that can sometimes let you know that you may have done your math incorrectly. You may look at it and be like, that doesn't solve that way. I think I made a mistake somewhere. So just, be aware of that. So the first thing I'm going to do is add this 0.09 to both sides and simplify this a little bit. So now I have 0 equals minus 5 meters per second squared times time squared plus 0.39 meters per second times time plus 0.9 meters. And you'll always see this pattern where you have meters by itself. And then here you'll have meters divided by seconds times time. So if if your time is measured in seconds, then your seconds cancel out. And then here, where time squared, you have seconds squared at the bottom. Now, I am not good enough at math that I can factor that. Oh no. So I'm going to have to use the special equation. So we're going to have time equals, let's see if I get it right. I'm not going to get it right. Do you guys have it memorized? Is it b or b squared? So it's minus b plus or minus the square root b squared minus.
Good morning.
Hello.
Hi, did Jane Watkins arrive?
Yes.
What about Neve? Did she arrive?
Yes. And she waved at you.
What?
She waved hello through the computer to you.
Okay, well, I know she was having power issues this morning.
Oh, was she? Okay. It was very windy yesterday.
Yeah, so she hasn't been able to log on yet?
No, she's there.
Oh, she's there. Okay, great, thank you.
Okay, thanks. All right, did I get it right, Kim? Okay. I'm always worried that I'm going to do that one wrong, so I tend to look it up. All right, so we're going to fill this guy out. So our time is going to be equal to, you guys all familiar with this one? We all done it before? That's why we have math prerequisites for physics, so I don't have to teach you guys this math stuff from scratch. So we've got minus 0.39 plus or minus, I'm going to wait for a second to draw my square root, but 0.39 squared minus 4 times minus 5 times minus 0.9 divided by, I'm just going to write minus 10 down there because I know that that's what that is. All right, so minus 0.39 plus or minus. So we've got 0.39 times 0.39 minus 4 times minus 5 times minus 0.9. I'm concerned about that number. We can't have a negative number in there. This is why. This is a positive number. See what I mean? Like you can do these and you can kind of be like, oh, that's not right. If I get a negative number for what goes under here, I must have done something wrong. So we got minus 4 times minus 5 times 0.9. That value right there is 18. So 0.39 times 0.39. Oh, it's positive 18. Hold on. I blew it again. Okay, so I got 18.15 divided by minus 10. All right, so I can either have something with the positive value here or the negative value. So if I've got minus 0.39 plus the square root of 18.15 divided by minus 10, if I use the plus sign, then time is equal to minus 0.39. So that would be telling us we're going back in the past. So up here, for that to be true, if our equation describes a parabola, that ought to be describing that point in time. If we extend the parabola, that's where it should be. So should we expect our next number be bigger or smaller than the absolute value 0.39? What do you guys think? Is this more than halfway across the little parabolic arc? If it's more, well, because if we imagine, you see what we're imagining here? Oh, you're gonna head out. Okay, good luck. Enjoy your cookies. Thank you for your service to our community. So if we're more than halfway past our parabola, then we would expect that this time is greater than the time left. So I'm actually expecting we're going to have a smaller number here when we use the negative sign. So we've got minus 0.39 minus the square root of 18.15 divided by minus 10. Ooh, we got positive 0.46. Yeah. Okay. So now I'm wondering if I did something wrong. What do you guys think? Did I do something wrong? Four. or 6. Hmm. Point. I'm still skeptical about this. I feel like I did something wrong somewhere. Do you guys see anything I did wrong? Yeah, I was just double checking our equation. Our equation is correct. Okay, so then our question is, do we do one of these wrong? Vertical, use the sign, opposite, 15. Point 38. So that is correct. I'm not sure. Something about this tells me that it's not quite right, but I'm not sure. Not sure. I'll have to think about that some more. We'll just move on for now. And then if I figure out if something is wrong with that, we will deal with it later. But we're going to need to choose the positive one going forward for how long it's going to take to fall. Let's put a 0.46 seconds there. It's going to be the same here. Back already? Yep. Awesome. Thank you. Yeah.
For initial y velocity, I did sine times 20, or sine is 20 times 1.5.
Why sine 20?
Oh, I'm on the wrong button.
Okay.
I was confused. That's what I did.
Cool.
Like, I did what you did. I just read the wrong button.
No, that's fine. I'm just like, I'm a little perplexed about it still. So I'm like, well, we're just going to go forward with it, but I can't figure out what's up with it that's not working correctly. Maybe it's correct and I'm just drawing my picture wrong. Like, I don't know. Is that an option? Oh, I know what I did. I know what I did. Okay, do you guys see it? This right here, my initial vertical velocity should be negative because it's downward, right? So if that's negative, then over here, this number should also be negative. If that's the case, then right here, this should be negative, right? So that this number then is positive. I mean, here it doesn't matter so much because it's squared, right? So that it wouldn't matter. But if this number is positive instead of negative, We do 0.39 plus the square root of 18.15. Then when we do the positive, we end up with plus 0.46. And I bet when we do it the other way, we get the other one. So 0.39 minus the square root of 18.15. And then I got the negative value. So if I divide that by 10, then I'm going to get negative 0.39. So there we go. Based on our figure, our answer didn't match. And so there was a problem in there. And what it was is that I had forgotten to use the correct sign. So I'm going to change, yeah, so 0.46, do we want that? Is that really 39? It's kind of an interesting thing. Oh, this one's going to be plus 38, and this one would be, yeah, now I got to get my signs right down here. Okay, so if we use the positive sign in our quadratic formula, we would end up with minus 0.46. If we use the negative sign, we end up with plus 0.39. 0.39, 0.39. Okay, so now we can finally figure out our horizontal range. So to figure out our horizontal range, what we need to do is our range is equal to time times our initial horizontal velocity. Our time was 0.39 seconds times 1.45 meters per second. 0.39 times 1.45. So I've got 0.57 meters. So that tells us that our object is going to hit the ground after traveling 0.57 meters. Whew, how'd you guys do? Did you get that one? Oh, it took me 2 tries. Did you get most of the way there? Did you guys get the times? Did you get the range? Shannon, did you get it? No?
I did what you did at first.
Dang. I know. Like, see, that's how common it is. Like, I do the same problem every year, and I blew it, and I screwed up the signs. So, yeah. But, like, that's kind of why I show you guys, too. You know, like, we can estimate. You know, we went up here and we said, well, if this is a parabola, and we're going to say that it should take less time in the positive direction, then we come down here and we don't get that answer. It tells us we did something wrong, you know. So I don't know. I kind of like modeling that for you guys so that you know that, you know, one, even experienced people make those mistakes, and two, there's ways that when you solve the problem, you can get to the end of it, you can be like, wait a minute, I know that I made a mistake in here somewhere, because I think that that's valuable, you know. Okay, we'll try to do number 3. Did you guys like number 3? Do you like to think about water balloons hitting stuff? No. It's almost summer. Water balloon. No. Okay. So it says a water balloon is launched at a building that's 24 meters away. So we know that the distance between this point and this point is 24 meters. We know that we have an initial velocity of 18 meters per second at an angle of 50 degrees. Look, him. And this is at what height will the balloon strike the building? So here's the thing about this problem. And I know this because I've done this problem more than once, but I don't know if you guys noticed this. There's 2 ways you could hit the building. You could hit the building on your way up, or you can hit the building somehow on your way down. You guys see that? So there's the possibility of 2 different ways that you can hit the building, and we have to figure out what height. So if we want to solve for what height, we're being asked to solve our change in vertical position. So what we need to do is make a list of our variables, things that we know. Our horizontal things that we know is that our range is going to be 24 meters. We don't have our initial horizontal velocity, but we could figure that out pretty easily. For vertical things, we've got that we are trying to find our range. We know that acceleration is minus 10 meters per second squared, and we could find our initial vertical velocity pretty easily. So let's figure out what the components of velocity are. So again, if we've got our angle with 18 meters per second at 50 degrees, our two sides here, we're going to have our initial horizontal velocity and our initial vertical velocity. And I know from my prior experience, the VIX is going to be 18 meters per second times the cosine of 50 degrees. Do you guys see how I did that? It's just from that pattern that we were using before. We know the trig relationship is that it's the cosine, and we know that our hypotenuse is at 18 meters per second. So we can just go straight to this if we want to. So 18 times the cosine of 50 degrees is going to be 11.6, oh, that's an ugly 6, meters per second. And our initial vertical velocity is going to be 18 meters per second times the sine of 50 degrees. Sorry, my 50 is kind of messed up. So 18 times sine 50. 13.8 meters per second. I can put these down here in my lists. I should be able to solve a time here. So if I can solve for time, then I can use that on the other side. So the time is going to be equal to, let's see, if position equals velocity times time, time equals the change in position divided by velocity. .07 seconds. So then if we want to find our vertical displacement, 1/2 times minus 10 meters per second squared times 2.07 seconds plus our initial velocity, 13.8, running out of space, times our 2.07 seconds. So 0.5 times minus 10 times 2.07. So we got minus 10.35 plus 13.8 times 2.07 to 8.6. So it's going to be 18 something. Yeah, so we got 18.21 meters. Is that what you guys got? We have consensus about that? So we think that it hit the building 18.2 meters up. But I actually don't know if it's on the way up or if it's on the way down. I don't know. So the second question says, if the balloon misses or shoots over the building, how far will the building land from its launch location? So for this problem, just imagine that the building isn't there. Does that make sense? Like it says, like we're not told how tall the building is, right? We're just told that it's 24 meters away. What if the building isn't that tall? What if instead the building is only this tall? Right? Then it wouldn't hit the side of the building. It's going to go over it. So what we're going to do here is figure out, what this range is. So we're going to pretend like we don't know about this 24 meters. So now we have to think about a different list of variables. So the things that we know our velocity still, right? Those are going to hold true. So our initial horizontal velocity is 11.6 meters per second. Our initial vertical velocity is 13.8 meters per second. We also know acceleration is minus 10 meters per second, seconds squared. Um, and we know some other stuff here. So if our balloon goes all the way over, then we can start looking at, do we want to do the halfway point or all the way? Which one do you guys like? Do y'all have a favorite? Maddie?
Wait, I have a question.
Yeah.
When you found the change in y, does the first 2.07 not have to be squared?
Oh no, it does need to be squared. Good eye, Maddie. Okay, so you guys see what Maddie said? She's like, "Hey, doctor, you're wrong. This one needs to be squared right here." What? That's completely valid, right? This is what we do in science. If we ask around, be like, "You guys know that Einstein did this? Are you guys aware of that?" So when Einstein wrote his theory of relativity equals mc squared, he was actually, he was married to a woman who studied physics in college, which, firstly, in that period of time was kind of incredible. But his wife literally edited his papers for him. So he would give her his papers first and be like, "Does this look right to you?" Do you guys do that with your friends when you do homework? Be like, "Can I look at your math? I just want to make sure that mine is right." Yeah, right? And so scientists do the same thing. And so if I look up at you guys and I'm like, "Yeah, does that seem okay?" But Maddie's in the back going "That's not okay." That's fine. Okay, so we have to fix our math. So let's see. 2.07 times 2.07. And I'm still distracted because I didn't get nearly enough sleep last night because of the stupid wind. It was so windy at my house. Minus 10 times 0.5. All right, so it should be minus 21. That's substantially different. Maddie saved us. All right, so now I've got minus 21. I'm going to add 28.6. Now I have 7.2. Is that better, Maddie? Okay, awesome. 7.2 meters. That's a more reasonable height for a building, I think. Okay, so now we get 7.2. So down here, the one that I like to use is the halfway point. Do you guys know why? I have to do an extra step at the end by doubling the time. But if I use this halfway point, then my vertical velocity is 0. And then I don't have to use the quadratic formula. Do you guys like using the quadratic formula? If you do, then you can go here and say that my change in position is 0. But I like doing it for this one. So what I would do there is I would say that my final vertical velocity is 0 meters per second. And that gives me enough things that I can solve for an equation. The equation I'm going to use then is going to be the more I have final velocity squared equals initial velocity squared. Oh, no, not that one. Final velocity equals initial velocity plus acceleration times time. Way simpler. So now I've got 0 meters per second is equal to 13.8 meters per second plus minus 10 meters per second squared times time. And then all I have to do is solve for time. So minus 13.8 meters per second equals minus 10 meters per second squared times time. So we can do this in our heads almost, right? So time is going to be 1.38 seconds. And that's halfway across. So if I wanted to go all the way across, then my total time is going to be 1.38 times 2, which is 2.76 seconds. So I wrote this on my list. I marked that as t, and then I put 1/2, so that I know that I mean that time is only to this point. This is my t 1/2, and this is time. So then I can take this number and apply it to my horizontal stuff. So if my time is equal to 2.76, then my range is going to be 11.6 meters per second times 2.76 seconds. I forgot my units. I got 32 meters. Did I do okay on that one, Maddie? Awesome. Okay. I'm feeling better about myself now. Do you guys have any questions? No? I feel like there's nobody in this room. Where'd everybody go? Hi, guys at home. It's like blood drive and stuff, so there's a bunch of folks not here. All right, we'll finish up the balloon on Monday. Woohoo! Enjoy your weekend, everybody. See ya. Have a good one.